So good afternoon. It's a real pleasure and honor to be here. I've been in Thailand many times with my husband and my 2 kids, and it's a beautiful country and beautiful people. So today, I'll tell you about Nano, and I'll start with this one. So imagine this ball is an atom. Then in reality, it would be 10 million times smaller. And if I placed 7 of these atoms next to each other, you would have 1 nanometer. Now, if I offered you 1 gold atom per second we have had since the Big Bang, since the birth of our universe, would you be able to make a necklace of gold today? What do you think? Would you have enough material? No. In fact, you would have less than 1 milligram of gold today. So atoms are small, but we can see them. I'll show you. So I'll show you 2 things today. I'll show you that we can see atoms, we can see at the nanometer scale, and when we can see, we start to understand how materials are working, and then we can design even better materials and build them. Secondly, I'm going to show you that you can actually repurpose technologies that have already been disrupted. They're available at a low cost. But first, I would like to share a story with you. It's a story on Zika and dengue. So Zika and dengue as well, they're unfortunately spreading. If we now stay with Zika for a while, there's still no cure, and there's still no vaccine. We also know that Zika is spread by mosquitoes. And it's also known now that it's sexually transmitted and that the virus can stay alive for up to 6 months in semen. So you might be spreading the disease without knowing that you're a carrier. Now, if you got the Zika virus, you might just get a slight fever, and within a few days you're back to work. But what if you had been pregnant? Then it would have catastrophic consequences. It's known that Zika virus can cause neurological disorders and changes in head shape. Now, if you were worried that you were carrying the Zika virus, you could go to your family doctor. The family doctor will take milliliters of blood from you using a syringe and send it to a centralized lab. In the lab, they have these huge lab centrifuges where they clean up your blood, so they only look in your blood plasma, and they will be looking for tiny biomarkers that you only have in your blood if you're carrying the virus. And within a week, you'll get the response back. A week can be a very long time to wait. But if you are living in a place like this, you do not have access to diagnostics. And you don't know how to plan your pregnancy. And you don't know if you're spreading the disease. So what can we do? Any of you still has a DVD player at home? You can be honest. I have one. What about a Blu-ray player? What about a PlayStation? PlayStations? Come on. Okay. You're really not that old-schooled. You're really high-tech. I'll show you. Have you tried to take a Blu-ray player apart? Have you looked inside it? It actually has 3 lasers inside, and the lasers can read data track with a height of just a nanometer. And there's a motor that can spin the disc super fast. A lot of cool technology available at a very low cost. So now I'm going to put nanoparticles on one of those discs to detect Zika virus. So now this is a particle, it's magnetic, and it's around 100 nanometers in diameter. On the surface, we have coated it with capture molecules that will capture the biomarkers you have in your blood if you're carrying the Zika virus. Most of you are not carrying the virus, so if I'm looking for this virus biomarker in your blood, nothing will bind to my particles. They're just going to swim around in your blood plasma from your blood sample. But if you have the biomarker, the green molecules here, they're going to capture these green molecules, and they want to capture the same molecules, so they're going to cluster together. And now this big cluster we can see, not by the naked eye, but by turning on the blue laser in your Blu-ray player. Because when the light is going to travel through your blood sample with the particles, the light is going to travel differently because the particles are now bigger. So we're not looking with our eye, we're just looking with the blue laser from the Blu-ray player. So this is a prototype from our lab 4 years ago. You take a disc that you have engraved channels inside, take a prick, blood from your finger, place it on the disc, spin it to centrifuge your blood sample so you separate out only your blood plasma. Transfer that to a different chamber on your disc with the preloaded magnetic beads. And then you incubate, turn on the blue laser from your Blu-ray player in the back, and you have the yes or the no on Zika virus in 2.5 minutes. So this is the technology that has now been spun out to a company called BlueSense Diagnostics, and they're selling their products. And the first country, I'm happy to tell you, where they actually sold this device for dengue fever detection was here in Thailand. And second country is Malaysia. And it only took 4 years from research to a product that they're selling because they have repurposed technology that was already developed. And this is, by the way, my former PhD student, Filippo Bosco, the CEO of the company, being interviewed in Danish television. So what did I just show you? I showed you that you can repurpose technologies that are already out there. And secondly, it's about going across disciplines. So in this case, we took pretty high-tech nano bead and combined it with an old-school DVD disc that we have made some channels on, and then we applied it in the medical field. Now I've shown you that we can see nanometers indirectly using a laser, but we can see smaller things than that. We can actually see atoms. And this all started back in 1981 by these two researchers from IBM Zurich. It's Heini Rohr with the white hair and Gert Binnig next to him. They had made a super microscope called the scanning tunneling microscope that could see atoms on a surface. And when they first published their paper, very few scientists believed them. They were actually laughed at, but they continued. Another interesting thing is that they were not working in surface science when they made this discovery. They were working in superconductivity. So sometimes the greatest discoveries, they actually come from people who are brave enough to kind of step outside their own comfort zone and seeing the challenges from a new perspective. So Heini, unfortunately, he passed away back in 2013. And that year, IBM released this little video I'm going to show you. The video is made by atoms. Each point on a surface is a single atom. So this microscope can see atoms, but it can also pick them up and place them somewhere else. So this movie has been made by looking at atoms on a surface, taking some of the atoms and place them somewhere else, take a new image, place some atoms a new place again, a new image, and then they stitch all the images together. And then in the end, they have an animated movie made by atoms. And in this case, it's a movie about an atom and a boy. Of course, this is more for fun. So I'm going to put my atom away for a little while. It's going to come back. So we can actually manufacture at the atomic level, at the nanometer level. But 1 nanometer is 1/1,000,000th of a millimeter. So how on earth do we do that? Well, we can do it in 2 ways. We say we can do it bottom up, or we can do it top down. Bottom up is more like working in a chemistry lab, where we ask the molecules themselves to build something fancy for us. Top down is more what they do in the computer chip industry. They start with silicon, and then they remove material and add material until they have a three-dimensional component, for example, with a lot of nanowires in it. An example of bottom-up manufacturing is this DNA origami. So today you can design any DNA sequence you like on your computer, and within a week you can get it shipped to you. And in this way you can design DNA that will fold itself just like paper origami. So DNA has 4 bases, A, T, C, and G. And if you know that, you can make DNA strands that will fold itself in any shape you like. So it can be boxes, circles, smiley faces, as you'll see. And it all starts just by pouring the DNA into a solution, and then it's going to assemble itself. It does so by having some small clips, the small strands you can see that will connect to specific places inside the DNA strand and hold it all together. So here you see building a box, building a smiley face, or you can also build small boxes with lids on in a nanometer regime that can open and close to deliver drugs in your bloodstream, for example. It's all possible by asking the molecules themselves to do the manufacturing. If you want to work the other way, so top-down, that's what they do in the computer industry. And to do that, you need to be working in a super clean environment. So this is a much more expensive manufacturing technology. And you have to dress the people who are handling all this in clean room suits you can see here. I'll show a little video from Denmark just to show you how it is to work in there.
DTU Danjib is the national centre for micro and nano fabrication in Denmark. We have 1,350 square metres of cleanroom facilities. Here, researchers, technicians and engineers from universities and companies can do research and develop and manufacture high-tech microchips. Microchips for better health, alternative energy and a faster internet. Production of chips with structures in the nanometer range requires high-tech equipment with extreme precision. We have equipment that can write text with a font size of just 50 nanometers. So small that you can write the entire Bible 2,000 times on an area the size of a single grain of rice.
So, now you got a short introduction to the ways we can manufacture at the nanoscale. So I've collected 8 examples for you, covering different aspects. And the first example is in Catalysis. It's a collaboration between a company called Haldor Topsøe and University of Aarhus in Denmark. So in Catalysis, you can make chemical reactions happen that would never happen if they didn't have this surface to sit on, the catalytic particle. You, for example, all have catalytic particles in your cars if you're using a normal gas car, because this is used to desulfurize the exhaust, so we don't have sulfur rain anymore. So this company are earning a lot of money on selling catalytic particles. And when these new super microscopes appeared, they wanted to see how are these particles actually working. And what you can see behind me is a scanning tunneling microscope image of such single particle, and each bump is one atom. And much to the surprise, this company realized that the entire particle is not active. It's only at the edges that it's active, where it's yellow. And when you see that and you understand that, then you have the possibility to design new catalytic particles that are much more efficient, and then finally to build them and sell them. And by doing something like this, the company increased their market share from a few percent to 40%, because they really increased the efficiency. Now, catalysts are everywhere, and now you can actually, using catalytic particles and something called an electrolysis cell, you can make ammonia just from air and water, and then doing catalysis. So you're taking nitrogen out of air, and you're taking hydrogen out of water, and then you can create ammonia, which is used, for example, a lot in fertilizing fields like rice fields. Second example, cleaning. Wouldn't it be nice if we never had to clean our cars, our windows? We never had to take the big container ships out of the water to remove whatever is growing on the sides. Well, the lotus flower has figured this out. It can't get dirty. So if you throw mud at the flower, it's going to stay white. And now we have the tools to actually see how it's doing it. So if you look to the left, this is real images of the flower. It's nanotextured at different levels. And this way of being nanotextured prevents the water to actually get a grip on the surface. It will stay as a water droplet on top. And then eventually the water will roll off. And as the water rolls off, it's going to take the dirt with it. So it's self-cleaning. To the right, you can see a replicated surface in polymer with the same features. This is something we can do in polymers, and then we can make these super hydrophobic surfaces that can't get dirty. Next example. Have you seen this situation? You're driving, and you have water droplets everywhere on your windshield? Or yesterday when I arrived in the airport in Bangkok, we were picked up by a bus. And just riding to the terminal, I couldn't see anything. It was all foggy because of the heat difference between the inside and the outside. So imagine you could just see out of your windshield all the time. Well, you can do that by nanotexturing a surface such that water will actually creep in between the nanotextures on your surface, and then it will move and wet the entire surface. It's called nano-wicking effect. It's using the pillars to kind of move in between. And then you can generate surfaces that will always wet evenly everywhere, and then you don't have these changes in coloring. Then this one, it's making colors without chemicals and without pigments. This is a morpho butterfly. It's beautiful blue. It lives in the rainforest. And if you step a little bit to the side, the blue is going to change a bit. If you look close, you'll see that it's using nanotechnology. The wings are nanotextured. It's like small Christmas trees, and the spacing between material in the wings is around 200 nanometers. It corresponds to the wavelength of blue light. So when you illuminate the wing, all colors will go through what's called disruptive interference. Only the blue color will come back to you and you can see it. And that's what makes the color. And this is something industry has been using. To kind of interesting examples coming here.
Blue, midnight blue, royal blue, deep dark blue, all breathtaking, yet nature has produced another blue, a miraculous color so unique that it belongs in a category of its own. The structural blue of the morpho butterfly. It took nature tens of thousands of years to create this structural blue color.
Structural color is the designer's dream technology. By using this, we bring to life the rich curvature of the LC body.
So I think that you can do it with a car, but there are many other aspects. Imagine you can color plastics without chemicals. Then you can do it in toy manufacturing, and you can actually integrate the nanotexturing into any molding of plastics, like injection molding, for example. So then it opens up for a lot of new perspectives. My next nano example relates to cooking over open fire. So still today, around 3 billion people cook over open fire. And according to WHO, around 4 million people each year die from diseases related to inhalation of the particles from the cooking. Also, it needs a lot of wood to fire, so it leads to deforestation and desertification. So many people are trying to help here. And I've taken one example from a startup company called Heliac. What they do is that they make a solar cooker and sell it at a very low cost. What you can see on the image is that they're using a polymer foil to concentrate sunlight onto a mirror and up to a cooking plate. And then you can actually start cooking. People are sending the dishes back to the company just to share what they've been cooking using this device. And it works even in Denmark. So then it works everywhere, I'm pretty sure. But how come, actually, that we can concentrate, I'll move back one, that we can actually concentrate light by just having a polymer sheet? Have you tried to concentrate light? Have you tried to burn hole in stuff with a magnifying glass? Yeah, you have. You remember the magnifying glass? It has a curved structure and it's pretty heavy. But it doesn't need to be like that because there's something called a Fresnel lens. So to the left, you see the conventional lens, your magnifying glass. But to the right, you can actually texture the polymer or the glass so that sunlight will be focused into one point. That's called a Fresnel lens. And doing so, we can replicate the lens structure into polymer sheets very cheaply. We're using a manufacturing line called roll-to-roll manufacturing. So the Fresnel lens itself is made in clean room, but you only need to make one. That's our master. And then by this foil manufacturing, we're replicating the nanotextures into kilometers of polymers so that we can make hundreds of millions of these solar cookers per year. Then it's really being translated to something that you can use. My next example relates to printed electronics. You have heard a lot about 3D printing. You can also print conducting, semiconducting materials. And you can also use a normal printer to print some of these materials. But in order to print these conducting materials, you need inks that are conducting. And they are made conducting by mixing conducting nanoparticles into the ink you're using. Because then you can still print it, and it's flexible. So if I print on my clothes, I can wash it, and it's flexible, it won't break, because there's a lot of small particles interconnected. I have a few examples from Joseph Wang's group in Santa Barbara. He's printed this device on socks, and they generate energy when you have sweaty feet, because it's using the salt in the sweat to generate energy. And then you can power devices in your underwear that's monitoring the salt concentration in your sweat, because this is going to tell you about your well-being, how stressed you are, for example. Some of these devices you can already buy. You can buy shirts that will keep you warm if you're skiing. They have integrated electronics in them. And there is this design company called Cute Circuits, where you online can buy a dress with a lot of woven-in wiring, and then it has LEDs and sensors inside it. And using your smartphone, you can change the look of the dress. Yeah, it's kind of cool. But you can print more than that. You can print solar cells now. You can mix in perovskite crystals, and they're actually pretty good solar cells. So then you could print a solar cell on your hat to power the rest of you, if you like. Doesn't stop here. Of course, you're going to print on skin. And you're going to print Band-Aids. So I have a little video from Japan for you here.
I'm Takao Someya, a professor at the University of Tokyo. Our on-skin sensor utilizing nanomesh electrode is ultra-thin, lightweight, stretchable, and breathable. It is capable of monitoring health conditions simply by pasting it onto the skin. New sensor can be worn on the skin continuously for a week without causing any inflammatory issues. Our skin display is a 24 by 16 array of micro LEDs, and it exhibits simple graphic with motion because it is made from thin and soft materials. It can be freely deformed. The skin display also showed an electrocardiogram measured by using nanomesh electrodes.
So, my last two examples relate to biology. I actually stole one of Heini Rohr. You remember the guy with the white hair and the microscope from IBM? He was a really smart guy, and he made this slide many, many years ago. And he said that at some point, our top-down manufacturing, so all the dead materials that we make smaller and smaller, they're going to be so small at the nanometer scale that they can interface with biology, which is more the bottom-up approach. And this is where we are right now. So there's a lot of things happening in the interplay between dead materials and living materials. And I could have had just a full talk just on this topic. I've taken 2 examples. The first example is from Dresden. Oliver Schmidt is his name. So he's making these really, really thin integrated circuits. They are so thin that when you release them from the underlying substrate, they curl up and become 3-dimensional. And when you do that, you can make micro robots. And this example is a sperm bot. So it's helping sperm cells to swim that can't swim, which is a problem. I don't know about Thailand, but in Denmark, actually, infertility is becoming a real problem. I'll just show you the robot here. So it's coming. It's manipulated with magnetic fields. It's catching a sperm cell, and now it's fertilizing. It's moving. Yes, happen. And then you can retract, and you can try again with another one. So that was one interface between dead and alive materials. The other one is an example that came out just like a month ago. It's a collaboration between Chinese researchers and American researchers. And I'm just thinking, you know, wouldn't it be cool if we could see more than our eyes allow us to see? Imagine you could see in the dark. So if you look at the electromagnetic spectrum, the visible range is tiny. Imagine we could see a lot more. Maybe it would be scary, but of course, it could also be cool sometimes, maybe. So what the researchers did was that they made mice see in darkness for 10 weeks. And what they did was that they took particles, nanoparticles, and inserted them in the eyes. It was just like droplets or injection. And the particles went to the back of the photosensitive part of the eye. And they were made so they can do what's called upconversion. So they could take 2 photons of infrared light and convert it into the visible light regime in the eye. And then by testing the mice in different mazes, whether they could find the food in darkness when they could only see with infrared light, or if they were only guided with infrared light into, you know, a swimming pool and they had to swim out of it, only the mice that could see in the darkness were able to get out of these mazes. The effect lasts for 10 weeks. And they can see visible at the same time in the visible regime. And there seems to be no harm done. So, of course, there are many applications. I'm sure also some military applications here. So that was my last example. How fast is this going? Well, I've been in this field for a while, but I'll just show you this one. The first Fresnel lens was installed in a lighthouse back in 1823. It was made in glass, and it was made to send light out to the boats. The first Fresnel lens made in a clean room environment came out in 1998. It was made super expensive technology called X-ray lithography. And I thought personally, it's never going to be used for anything. But then comes new development, and then someone figures out why not just emboss it or use roll-to-roll manufacturing that's used in food industry, and then we can make kilometers of polymer foils with Fresnel lenses. And now we can make solar cookers with nanostructures inside and sell it in Africa. You might also think, I'm never going to see nano. The university here is not going to afford nano tools. But that's also not true. People are hacking nano now. So you can build your own little atomic force microscope, which can actually see at the nanometer scale. By buying this equipment or something similar on the internet, assemble it yourself, and then look at nanometer structures. And the core part here is actually using a pickup head from a DVD player as a readout unit. So what's coming in terms of manufacturing? I think that you're going to see a merge. It's not going to be just 3D printing or injection molding or nano imprint lithography. It's going to be all sometimes combined at the same time. This is a combination of imprinting with nano and roll-to-roll manufacturing. This is an example of a 3D printed implant, but then they have embossed nanotextures into the 3D implant so that it looks more like what it would look like in the real life, so that the cells likes to attach to it. And finally, the way we make materials today is going to change. Today we do a lot of chemicals by oil-based methods. But you can actually ask bacteria to produce a lot of the chemicals for you. People are also now modifying bacteria with nanoparticles. So you have like a cyborg. It's a combination of, again, dead materials and bacteria. So I'll end here. Thank you very much for your attention.